This video is on the topic of the quadratic formula. We're going to use the quadratic formula to solve quadratic equations. This is what's considered the brute force technique for solving a quadratic equation. It will essentially work on any quadratic equation you can think of. So all of the equations in previous videos, we can actually use this formula to solve them. So we're going to take also what's called the discriminant approach. And if you look at the formula I have down here, if ax squared plus bx equals c equals 0, then x equals, and then we have this elaborate formula. Now, we're going to focus on just the b squared minus 4ac first, because that is called the discriminant, and it predicts the nature of the roots of your equation. And the nice thing about focusing on that, that's kind of the hard part of the formula. So if we can get that figured out, then most of the work is accomplished. So that's the approach we're going to take. So this is known as the quadratic formula. And we have to have the equation in what's called standard form, and that's the ax squared plus bx plus c equals 0. You want 0 on one side of the equation and basically everything else on the other side. So that's going to be our guide, this formula and this standard form. So let's start with an example. So we have 3x squared plus 11x equals 4. We want to know what x is. Now you probably already know from previous videos or other lessons that the exponent of 2 reminds us that there should be 2 roots to this equation. And typically, quadratic equations will have 2 roots. Unless a certain thing happens with the discriminant, and we'll talk about that. We probably won't show an example of that in this video, but we'll talk about it. All right, so let's go ahead and solve this equation. Now, in order to start solving this equation, we need to have the equation in the right format. So we need to get it in standard form. And you'll notice that we don't have 0 on one side of the equation. We have most of everything on one side of the equation, but that 4 needs to move to the other side. So we're going to go ahead and move the 4 to be on the same side of the equation as the 3x squared plus 11x. So we're going to use additive inverses to do that. So we're going to use algebra to show it. So we're going to actually subtract out the 4 on both sides. And because I am using the additive inverse, I'm going to go ahead and put a sum line in there. It's a nice visual. So that does leave us with 0 on that side of the equation, which is perfect. And then we have 3x squared plus 11x minus 4 on the other side of the equation. Okay, that's actually a little hard to read. Okay, so we're going to go ahead and write out all of the key factors for the discriminant. Ultimately, we want to calculate this bit. We want to calculate the b squared minus 4ac. This is called the discriminant, and this is the most important part of the process that we're doing right now. We want to figure out this thing. The discriminant predicts the nature of the roots to the equation, and it's the bulk of the equation, the hardest part of the equation, essentially. So we're going to go ahead and figure this thing out. So we're going to figure out what the parameters a, b, and c are. So the parameter a is the number in front of the squared part. So a is 3. And then the b is equal to 11. And then our c is equal to a negative 4. So that's all of the numbers that we need to put into the formula for the discriminant, the b squared minus 4ac. So we're going to go ahead and put those in, and then after that we use the order of operations to figure it out. So b is 11, but that's going to be squared, minus 4. The 4 is a formula constant, times a and c. Remember, when you do a substitution, you use parentheses to show that. So a is 3, and after we moved the 4, c became a negative 4. And then we just figured this out. So the square goes before anything else following the order of operations. So this is 121. 11 squared is 121. Notice how the signs work out here. The negative sign on the 4 will cancel when you multiply that to the negative 4 here. So you can multiply from left to right if you want. So negative 4 times 3 is a negative 12. And then a negative 12 times a negative 4 is our positive 48. Okay, add these together and we get 169. So that's the value of the discriminant. Now, of course, we haven't solved the equation yet. We haven't found the roots to the equation yet, but we found the discriminant, and that's the most important part. Now that we've done that, we have everything we need to run the formula. You know, the discriminant is the b squared minus 4ac. It's underneath the square root symbol. This is why this predicts the nature of the roots to our equation. The discriminant in this case is actually a perfect square. At this point, you should have a basic list of perfect squares memorized. 169 is a perfect square. If you run that through your calculator, take the square root of it, you'll get 13. So 13 times 13 is the 169. So since the discriminant came out to be a perfect square, that predicts for me that the nature of the roots of my equation, it tells me that the roots are going to be rational. We're going to get rational roots, which means the final answer is not going to include the square root symbol or anything weird like that. It's going to be rational roots, meaning nice clean integers or fractions. Or potentially it could be put in decimal form. So now we're ready to run the formula. So remember, I'm leaning on the formula in my thinking here. At this point, I'm saying, x equals a negative of b plus or minus the discriminant all over 2a. So that's what I'm using, and you might want to have the formula at your side when you're doing this. So we're ready to find the roots. X is equal to a negative of b, b is 11, plus or minus the square root of the discriminant, which is actually 169. So notice I'm not calculating all of that all over again. We've already worked hard to get that. And then it's all over 2 times a. A is 3. And then we just need to simplify this as much as possible. So we get x equals a negative 11 plus or minus. Remember, the 169 is a perfect square. The square root of 169 is 13. And then the denominator is 6. And we've got to remember, everything is over the 6. It's the negative 11 plus or minus the 13 all over 6. Now, when we simplify the roots to the equation, we're going to have to usually work with the properties of fractions. We might get lucky and get some nice integer values, but we might get some fractions here. But notice the radical symbol is gone. So that's why we know that there's rational roots to this equation. We're not going to involve the idea of a square root at all because we have rational roots. All right, now we have no choice but to apply the plus or minus at this point. So x is equal to a negative 11 minus 13 over 6. And we're going to figure out what that gives us. So a negative 11 minus 13, when you subtract from a negative number, it sends you further in the negative direction. So if you just add the 11 and the 13 together, we get 24. So this is going to be a negative 24 over 6, which gives us a negative 4. So now we have one of the roots to our equation. One of the roots is a negative 4. And it's a rational root. The discriminant predicted that. Now we have to use the other sign on this, the positive sign. So x is equal to a negative 11 plus 13 over 6. So a negative 11 plus 13, well, because they're opposite signs, we end up subtracting the 11 from the 13, we get 2. So here the positives beat out the negatives. So this is a positive 2 over 6. And that's an easy fraction to reduce. It reduces to 1/3. So now we can write all of the roots to the equation in a solution set. They're easy to write out in this case because we do have rational roots. So using set roster notation, x is equal to a negative 4 and the 1/3. When you list out the roots in a solution set, we write them in numerical order, how they would show up on the number line. So there's the two roots to our equation. So this equation, the 3x squared plus 11x equals 4, has the roots, the negative 4 and a positive 1/3. And we have rational roots in this case. All right, so let's try something that gives us a little bit different outcome on the roots. Maybe something a little bit more complicated. Okay, we're still going to be using the quadratic formula on this, but as you can see, the equation in its present form doesn't quite fit what we would call standard form for a quadratic equation. We got to get 0 on one side of the equation and everything else on the other side. So that means we're going to have to move that 33. So let's go ahead and move the 33 using inverses again. So we're going to subtract out the 33 on both sides. Technically, you can say we're adding a negative 33 to both sides of the equation. Putting a sum line in there because I am using the additive inverse. And then go ahead and figure out what we get. So we're going to have 3x squared plus the 12x minus, we got 12 minus 33. That's like 33 minus 12 in terms of how you would calculate that. So that's going to give us a 21. But negative 21. And then on this side of the equation, we get 0. Okay, so now we have the equation in standard form. We can go ahead and identify the parameters a, b, and c. Remember, a is the coefficient on x squared, b is in front of x, and c is the constant out there without a variable. So we'll go ahead and list those out so we can calculate the discriminant. So a is 3, b is 12, and c is equal to negative 21. Now let's go to work on this. So we're going to do the b squared minus 4ac. We're just focusing on the discriminant for now. That's the most important part of the whole process. Okay, so b is 12, but that's going to get squared according to the formula. The negative 4 is a part of the discriminant. It's a formula constant. And then we have 4 times a. So a is 3. So we'll do the replacement on there. And then c is a negative 21. And then now we do what we can to simplify this thing. And we're going to get kind of a large discriminant here. Ultimately, we're going to have to probably work with simplifying square roots quite a bit on this example. But 12 squared is 144. And then this is going to be a positive now because the negative sign in the discriminant from the negative 4 is going to cancel with the negative sign of c, or the negative 21. Negative times a negative is positive. So this is going to give us a positive 252. And then when we add these together, we're going to get 396. So the discriminant is fairly large. However, if you're familiar with the perfect squares up to a point, 20 squared is 400, so this is sort of close. But that's actually enough to tell us that 396 is not a perfect square. 361 is a perfect square. 324 is a perfect square, but not 396. So that tells us that the roots to this equation are actually going to be irrational. So we're going to have irrational roots. So they're going to involve the square root symbol for sure. Okay, now to simplify this, though, we do need to know a little bit about perfect squares and how to simplify a square root. We are in the business of looking for perfect squares, and at this point you probably have written those down in your notes, or you've seen them in the square roots video, the radical expressions video. So we're going to go ahead and just see what we can do with this, because I know I'm going to need it eventually. Or we can put it off until we need it in the formula. So let's just go ahead and run the quadratic formula. So now I'm going to go ahead and run the quadratic formula. So this is it. So we got to go ahead and put all the pieces together. We have the hardest part. We have the discriminant. So we're ready to go. So x equals a negative of b. So it's the negative of the 12 plus or minus the square root of the discriminant, which is 396. And it's all over 2 times a, or 2 times 3. Okay, so we have some work to get this simplified. This is going to be a negative 12 plus or minus. So the big challenge is finding that perfect square that divides the 396. The denominator is 6. So this is where the divisibility tests for 4 and 9 are very useful for us. The divisibility test for 4 is you look at the last digits of a number. If the last digits of a number is a multiple 4, the entire number is divisible by 4. Well, 96, you might not know if that's divisible by 4 or not, but if you add a 4 to it, it gives us 100. That implies that 96 is a multiple of 4. So 396 is divisible by 4, and 4 is a perfect square, so that's helpful. So 396 is divisible by 4. So that's enough information to know that I'm going to be able to simplify this in terms of square roots. Let's use the divisibility test for 9, which is another one of our perfect squares. Remember, the divisibility test for 9 is the same as 3, essentially. If you take the digits that make up the number, sum them together, if the result that you get is a multiple of 9, then the original number is divisible by 9. So if we add the 3 and the 9, we get 12 plus 6, it's 18. So 3 plus 9 plus 6 is 18. 18 is a multiple of 9. Therefore, 396 is divisible by 9. So 396 is divisible by 4. It's divisible by 9. And both of those are squares. Well, the product of 4 and 9 is 36. So actually, the biggest perfect square that divides 396 is actually 36, the product of 4 and 9. So it takes a little bit of work to figure that out, to figure that we can actually do that. And you can sometimes do a little cheat work with your calculator, but I use the divisibility test to figure it out. And if you actually divide the 396 by 36, you get the other factor, which is 11. So this is going to be 36 times 11. And then now we're ready to go ahead and simplify this as much as possible. We get a negative 12 plus or minus. The square root of 36 is 6. And then we get root 11. So plus or minus 6 root 11 all over 6. Now this ratio does simplify. Notice that the 12, the 6, the coefficient in front of the 11, the root 11, and the denominator, they're all multiples of 6. So this definitely reduces. We would use the properties of fractions to reduce it. So I'm just going to go ahead and do that. Now, in this case, you can use just what we use with common denominators to figure it out. Sometimes it's better to use a factoring and canceling approach. Probably should stick with that, so I'm going to go ahead and do that. I'm noticing that the 12, the 6 are both multiples of 6. So using the distributive property, I'm going to factor out a 6. So that's going to give me 6 times a negative 2 plus or minus, the 6 factors out, we just get root 11 all over the 6. And then the 6's cancel out, and we get x is equal to a negative 2 plus or minus root 11. So in this case, the roots are in binomial form. So one of the roots is x is equal to a negative 2 minus root 11. The other root is x is equal to a negative 2 plus the square root of 11. And we can go ahead and approximate both of these in a calculator. So when you're doing this, you're just basically following the order of operations. The square root symbol, in previous videos we saw that's also an exponent. So we would take the square root of 11 first. And for this root, we have the negative sign in front, so you can use a plus or minus key to make it negative. The 2 here is negative no matter what, so you can just go minus 2. Hit enter in your calculator or equals. You get a negative 5.316 roughly. And that's it. That's one of our roots. So this one's a negative 5. I'm going to go ahead and round to the hundredths place. So this would be 5.32. Make sure that you do this on your calculator so you can see how to do this to make this happen. I'm just going to double check it really quickly. I always tell my students to make sure they double check their results. So I'm doing that now. So it's looking good. So the other one is a lot easier to calculate because it doesn't have the negative sign in front of the radical. So we just take the square root of 11, get about 3.316, and then minus the 2 from that. And there's the other root. And if we round it to the hundredths place, it's 1.32, or roughly 1 32/100ths. Okay, so those are irrational roots, but what we did do is we did rational approximations to our irrational roots. But technically, the actual irrational roots are right here. This would be the exact values of the roots to the equation. You know, either x is equal to a negative 2 minus root 11, or x is equal to a negative 2 plus root 11. And then we just go ahead and, if we needed to make it real practical, do the rational approximations using a calculator. Okay, so that's the quadratic formula. Obviously, we need to look at other examples of this. So there's a follow-up video to this that's going to have 2 more examples in it. Thank you for watching, and don't forget the discriminant, the b squared minus 4ac. This is the most important part of using the quadratic formula. This is the best approach to take as far as calculating the roots to your equations.